Good morning, good afternoon, and good evening. We are Group 11 and we'll be presenting on Practical 4, which is about heat exchangers. Heat exchangers are units or operations that transfer heat between two fluids of different temperatures separated by a solid wall, with liquid being the fluid in this experiment. Two types of heat exchangers are employed in this experiment. These include the concentric heat exchanger and the plate heat exchanger, which was set up to run in the countercurrent configuration and the core current configuration. The temperature gradient, which is the difference in temperature between the streams flowing through the heat exchangers, facilitates heat transfer in the heat exchangers. The transfer of heat occurs by three principal means, which are convection, radiation, and conduction. Conduction of heat occurs within the heat exchanger as heat passes from the fluid with higher temperature to the fluid with lower temperature through the solid wall. To maximize heat transfer, the solid wall should be thin and made from a very conductive material. For this experiment, the plate heat exchanger and the inner tube of the concentric heat exchanger are both made of stainless steel, which is a better heat conductor than acrylic, the material of the outer tube of the concentric heat exchanger. The goal of this experiment was to show how heat transfer can be used to determine the performance of heat exchangers and, as a result, which heat exchanger is most efficient.
From having run the procedure, the overall heat transfer coefficient was determined and plotted against each of the flow rates measured from different configurations. The overall heat transfer coefficient gives an indication of how well materials are able to conduct heat. This is dependent on the thermal properties which define a certain medium or material, the surface area, and the thickness of the material used. Designing an optimal heat exchanger requires maximizing the overall heat transfer coefficient, and from the graphs obtained, it is clear that the plate heat exchanger attains a greater overall heat transfer coefficient as compared to the concentric tube heat exchanger. These conclusions align with the factors considered when deciding on the most efficient heat exchanger, i.e. the surface area prone to the exchange of heat of the plate heat exchanger is greater than that of the concentric tube heat exchanger. Hence, the plate heat exchanger is identified as the most efficient. When comparing the thickness of the two heat exchangers, the plate heat exchanger is less thick than the concentric tube heat exchanger, and this allows for a greater transfer rate of heat between the fluids. Hence, the plate heat exchanger, or to be more specific, the plate countercurrent hot flow exchanger would be concluded as the most efficient. From analyzing the heat transfer coefficient equations, the above conclusions are confirmed, indicating that the overall heat transfer coefficient has an inverse relation to the thickness and a direct relation to the surface area. The energy balance equation follows the first law of thermodynamics, which states that energy can neither be created nor destroyed, however, it can be transferred. From the results obtained when investigating the energy balance equation, steady state conditions were assumed and the shaft work was considered negligible. The results indicate that during the process of heat exchange, in all configurations, there was a loss of energy in the form of heat, which could be an indication of the presence of irreversibilities in the system or thermal resistance.
In an attempt to determine which heat exchanger configuration is best for optimal heat exchange, we compared the log mean temperature differences for each configuration. The log mean temperature difference is used to determine the temperature driving force for heat transfer in flow systems. It's a logarithmic average of the temperature difference between the hot and cold streams at each end of the heat exchanger. The formula for log mean temperature difference is indicated here in the image, where change in temperature 1 is the temperature difference between the hot and cold stream on one end of the heat exchanger, and change in temperature 2 is the temperature difference between the hot and cold stream on the other end of the heat exchanger. As indicated in the image, the log mean temperature difference can be calculated for both the co-current and counter-current configurations. A larger log mean temperature difference indicates greater heat exchange between the cold and hot stream. Thus, to decide which configuration provides optimal heat exchange, the log mean temperature difference would need to be considered. An analysis of the data revealed that all the concentric heat exchanger configurations had greater log mean temperature values, approximately 2 times greater than the values of the plate heat exchanger configurations. This means that the concentric tube heat exchanger setup is more efficient at facilitating heat exchange between the cold and hot flowing streams. For the plate heat exchanger, the configuration that enabled the greatest amount of heat exchange is the one where the fluids were flowing concurrently and the cold water flow rate was varied while the hot water flow rate was kept constant at 25 grams per second. Above all, the setup that enabled for optimal heat exchange is that of the concentric heat exchanger, where the hot water flow rate was varied and the cold water flow rate was kept constant.
The two fluids in the heat exchangers exchange heat, so the cold fluid will gain heat and the hot fluid will be losing heat. So the heat transferred will be calculated using the formula Q is equal to mCp change in T. Q is the heat transferred, m is the mass flow rate, Cp is the change in Cp is the specific heat, then change in T is the change in temperature. So the heat transferred for the cold side and the hot side is calculated and the average is obtained, and then the mass flow rate is plotted against the average heat transferred. From this we can be able to see the relationship between the mass flow rate and the average heat transferred. For the graph for the concentric heat exchanger, it is observed that as the mass flow rate of either the hot or the cold fluid is increased, the average heat transferred increases. And also, there's no significant difference between the graphs for the countercurrent and the co-current configurations. As you can see, the graphs are closer to each other. For the graph for the plate heat exchanger, the average heat transferred also increases as the mass flow rate of either the cold or the hot water is increased. And here it's observed that the graphs for the countercurrent configuration are above the graphs for the co-current configurations, which means that more heat was transferred on the countercurrent configuration. Then by comparing the two graphs, it's observed that the plate heat exchanger has higher values for the average heat transferred as compared to the concentric heat exchanger. Then looking at the plate heat exchanger, we observed that the countercurrent graphs are higher than the co-current graphs, meaning more heat transfer took place on the countercurrent configuration. Then from these graphs, we can conclude that the plate heat exchanger with the countercurrent configuration has the best performance compared to the other configuration and the concentric heat exchanger.
As mentioned before, this experiment was set up to demonstrate the heat transfer application within the two different heat exchangers, to demonstrate the performance of the heat exchangers, which then established which heat exchanger is the most effective. Therefore, in conclusion, the data collected and calculated overwhelmingly demonstrated that as mass flow rate increased, so did the overall film heat transfer coefficient. From the worked up performances, it is evident that the countercurrent flow of the plate heat exchanger established the highest performance of heat transfer, with its overall film heat transfer coefficient being 4 times the amount calculated for the concentric heat exchanger, and therefore becoming the best performing heat exchanger.